In perfect competition, firms are entirely beholden to the market. They are mere price takers, offering identical products to consumers who care only about finding the lowest cost. In 1883, mathematician Joseph Bertrand modeled what happens when a market consolidates into an oligopoly. He imagined a market where a few firms produce homogeneous goods and set prices simultaneously. On screen, two identical firm nodes compete for market share. With identical products, the firm with the lower price captures all of the demand. This creates a relentless incentive. Each firm undercuts the other by a fraction of a cent, driving the price variable down step by step until it hits their marginal cost of production. They reach a Nash equilibrium. The mathematical state shown here, P equals MC, dictates that the economic profit is exactly zero. This theoretical outcome contradicts empirical reality. In actual markets dominated by a few major players, we observe positive profit margins. The addition of a second firm rarely drives prices all the way down to marginal cost. Firms avoid the zero profit trap by employing two primary mechanisms: horizontal product differentiation and strategic collusion. The Bertrand Paradox serves as a strict mathematical boundary condition. It shows us what happens if firms compete strictly on price with identical goods, forcing companies to actively engineer market power to survive. To understand horizontal differentiation, economists use the Hotelling linear city model. This diagram establishes the initial spatial framework. Consumers are uniformly distributed along a line segment from 0 to 1. We place two competing firms at fixed opposite extremes of this line. Consumers pay a price to travel. This disutility is represented as a quadratic transport cost, denoted as Tx squared, where T is the transportation rate and X is the distance traveled. A consumer calculates their utility using U equals V minus P minus Tx squared. They weigh the gross value of the product, V, minus the price paid, P, and the travel disutility they incur. Somewhere on this line sits the marginal consumer, marked as X tilde. This buyer is strictly indifferent between firm 1 and firm 2, because the total cost of price plus travel is identical. Because consumers are uniformly distributed with a density of 1, the position of this indifferent buyer dictates market share. Firm 1 captures everyone to the left, giving them a demand function of D1 equals X tilde. Firm 2 captures everyone to the right, yielding D2 equals 1 minus X tilde. With demand defined, we construct the profit maximization function for each firm. Pi equals the price minus marginal cost multiplied by their specific demand. To find the optimal price, we take the first-order condition of the profit function with respect to the firm's own price. This mathematical step derives the reaction functions, showing exactly how firm 1 should price its good in response to firm 2's price. The intersection of these two reaction functions reveals the symmetric Nash equilibrium. Both firms will charge a price of P equals C plus T. The mathematics show that in this fixed location setup, market power is directly derived from the transportation cost parameter, T. Geographical distance acts as a shield against pure price competition, allowing firms to price above marginal cost without triggering the Bertrand Paradox. We can adjust this model by replacing the quadratic transport costs with strictly linear transport costs, meaning the disutility of travel scales constantly with distance. We also remove the assumption that the firms are identical. We introduce asymmetry into their unit production costs, where C1 does not equal C2. Under these unbalanced cost structures, the algebraic derivation of the indifferent consumer shifts. The equilibrium point moves away from the exact center of the line and toward the firm with higher costs. The reaction functions adjust to reflect a complex balance between geographical capture area and the cost advantages of the more efficient firm. In the resulting Nash equilibrium, the firm with the lower marginal cost leverages its efficiency to capture a structurally larger share of the market line. We expand the strategic complexity by removing the assumption that firms are fixed at locations 0 and 1, transitioning to an endogenous two-stage game. In Stage 1, the firms simultaneously choose their optimal geographic locations along the line segment, denoted as A and B. In Stage 2, the firms observe these chosen locations and simultaneously set their prices.
We solve this game using backward induction, analyzing the pricing strategy first to determine the optimal starting locations. When choosing locations, firms experience a demand effect. This creates an inherent mathematical incentive to move toward the center of the line, maximizing the baseline number of consumers they can reach. However, this is countered by the price competition effect. Moving closer together makes the products less differentiated, which incentivizes firms to move as far apart as possible to avoid fierce Bertrand undercutting. When transport costs are quadratic, moving close together makes price competition excessively fierce. The price effect strictly dominates. The result is a subgame-perfect equilibrium, where firms choose the principle of maximum differentiation, deliberately locating at the absolute extremes of 0 and 1. If geographical differentiation is insufficient, firms can turn to a second escape mechanism: strategic collusion. We can examine this through a three-firm differentiated Bertrand market. For this specific game, we operate under the baseline assumption that production costs are 0 for all three firms. This equation defines each firm's demand function. The summation term emphasizes cross-price effects. A rival's price increase directly boosts demand for firm I. Taking the first-order conditions yields the Bertrand-Nash equilibrium, logging the baseline profit, pi w, into our matrix. Now we model a cartel agreement. The three firms collude to maximize their joint profits, effectively setting prices as a single monopolist controlling the market. Solving yields an optimal collusive price, pk. The individual cartel profit, pi k, is mathematically greater than the baseline Bertrand profit. But we must test the stability of this agreement. We model firm 1 unilaterally defecting by calculating its individual best response while the others hold steady. By undercutting the cartel, firm 1 secures a deviation profit, pi a, strictly exceeding their share of the collusive profit. Because the immediate payoff of unilateral deviation strictly exceeds the payoff of collusion, the agreement is structurally unsound. Any static cartel in a differentiated Bertrand game is mathematically guaranteed to collapse from within. We can test if partial collusion offers a stable alternative by introducing a sequential Stackelberg variant to the game. In this scenario, firms 1 and 2 form a localized two-firm cartel. They act as the Stackelberg leader, publicly setting a joint price, PF. Firm 3 acts as the follower. It observes the cartel's committed price before setting its own best response price, PS. We use backward induction to solve this sequential game. We analyze Firm 3's best response to map the equilibrium prices for the cartel members and the independent follower. We then evaluate Firm 3's profit as an independent Stackelberg follower against the profit it would receive if it had simply joined a full three-firm cartel. The math reveals that riding free as an independent follower yields a higher utility than joining the cartel. The remaining firms are incentivized to break their localized agreement as well, proving that partial cartels are also inherently unstable in finite timeframes. To sustain a cartel, firms must change the parameters of time. We introduce the infinite horizon repeated game as the only mathematical mechanism capable of sustaining collusion. This introduces the discount factor, delta. It represents the shadow of the future, specifically how much firms value tomorrow's profit relative to the profit they can take today. We assume the firms adopt a grim trigger strategy. They collude indefinitely, but if any single firm deviates, it triggers an infinite reversion to the baseline Nash punishment profit for all future periods. This inequality defines the condition for stability. The present value of infinite collusion must equal or exceed a one-time deviation profit plus infinite punishment profits. Executing the algebra to isolate the discount factor, delta, the calculations resolve to a final threshold. The cartel holds if and only if delta is greater than or equal to 4/7. The Bertrand Paradox forces rigorous strategic action. Whether achieved by maximizing geographical distance between competitors or by leveraging the mathematical shadow of the future, market power is deliberately engineered. It is never an accident.